so you can stay in this room. You can take mine. Just go. Okay, so as I said, we are a little bit behind. I did not appreciate how much time it will take us to actually get into this room. So yeah, without further ado, the first talk is Nadav Cohen, and he will talk us about what trajectories, why should we think about trajectories of optimization algorithms and not only the properties of the stationary points.
Thanks a lot. So the title of the talk is Analyzing Optimization, Generalization, and Deep Learning Through Trajectories of Gradient Descent. And we'll start with kind of a recap or perspective on what the basic questions are for optimization, generalization, and deep learning, and then I will kind of state the main argument that I'm trying to make in this talk, and all the rest of the time will be devoted into trying to make the case for this argument. Okay, so at least in supervised learning, when we talk about optimization, we mean fitting training data by minimizing some objective, some loss function. And generalization refers to controlling the gap between our performance on the training data and on the test data. This could be achieved, for example, by adding a regularization term to the objective or a constraint. In classical machine learning, the basic theme, it starts off from the fact that the objectives are convex, usually. We choose models and problems such that the objective will be convex. There's usually one global minimum that's sufficiently attainable, and the choice of algorithm affects the speed at which you get to that minimum. But no matter what sensible algorithm you use, you will get to the same solution, so the statistical properties of that solution are irrelevant to the algorithm, generally speaking. In terms of generalization, there's a famous bias-variance trade-off, which qualitatively speaking states that if I apply more regularization, then the gap between train and test error decreases, but the training error will go up, and I care about the sum of these two things, the test error, hence there's a trade-off. Okay, on the other hand, if I make my regularization weaker, then the gap will open up, but the training error will go down. All in all, I think it's fairly safe to say that we have a reasonable understanding of what goes on here. Okay? In deep learning, the situation is very, very different. We allow the objectives to be non-convex. And there's not just one global minimum, there are a lot of them. And a priori, it's not clear that one could even reach them efficiently. But somehow, on typical problems, different variants of gradient descent seem to reach one of these minima, and we don't really understand why. And for generalization, the situation is even more peculiar. We know that, at least empirically, we know that some global minima generalize well. They have a low test error, but others generalize very poorly. And for some miraculous reason, on typical problems with typical data, if you use gradient descent or variance thereof, you often get to a solution that generalizes well. And maybe most surprisingly is the fact that there seems to be no explicit bias-variance trade-off. Peter talked about this. Okay? We can train huge models with a small number of examples without applying any explicit regularization, and we will generalize. And overall, I think most here would agree that we don't really have a good understanding of these questions, and that is why we're here. And the argument that I will try and make today is that maybe the language that we've developed for classical learning theory is not sufficient for understanding what goes on in deep learning. And in that case, I believe that a potentially fruitful direction is to look closely at the course of learning. And that means the trajectories of gradient descent. Study what happens throughout the optimization process. Okay? I will try and make the case for this argument through deep linear neural networks. Okay, that's going to be the basic theme of the talk. So without further ado, let's move to the actual content. The material that I'll present is based on 3 papers, one from the last ICML, one from this year's ICLR, and another one that's under review. My esteemed collaborators, which I'm sure many of you know, Sanjeev and Elad, and graduate students Wei Hu and Yuping Luo, and Noah Golowich, which was an undergrad, visited us last summer. Okay? So what's a linear neural network? A linear neural network, in deep learning jargon, is a fully connected neural network with linear activation. That just means that it's a mapping from input to output that is linear, but it's parameterized as a sequence of matrix multiplications. Right? So from a representational perspective, it only realizes linear mappings. There's nothing special about this. But in terms of optimization and generalization, this simple model is highly non-trivial. And it exhibits a lot of behaviors that are similar to what we see with nonlinear deep neural nets. And for this reason, it's often viewed as kind of a theoretical surrogate, and a lot of people are looking into this, including a lot of people here. This is just a sample of papers from the last couple of years. What we're going to start with is kind of summarize an analysis of the trajectories of gradient descent, or gradient flow to be exact, over linear nets. And then we're going to use those results for analyzing optimization and generalization. And along the way, we will see that using our trajectory analysis allows us to circumvent problems that one encounters if you try and adopt more traditional viewpoints. Okay? We're going to start with gradient flow. This is a continuous version of gradient descent. This is what you get when you take the step size to be very, very small. It's a differential equation, curve in space. At every point, your movement is in the direction that's opposite to the gradient. So if gradient descent are these discrete steps, gradient flow is this continuous curve. This thing is useful because it's continuous and it allows you to use a lot of mathematical machinery. And we will see how at least some of the results that we're going to derive, we're going to translate them from gradient flow to gradient descent. So gradient flow is kind of a theoretical stepping stone. Right? Now let's start talking about the trajectories of gradient flow over linear neural nets. Okay, so the kind of objectives that we're interested in have the following form. L is some loss over linear models. Okay, this could be L2 loss or cross entropy or whatever. Usually it's convex. And this kind of loss immediately induces an over-parameterized objective over a linear net. Okay, phi W1 to Wn, that is our objective over a linear net. The value, if you want to obtain it, just multiply the matrices by one another, get the end-to-end mapping, plug that into the original loss. So even though L is usually convex, phi is highly non-convex. Here's the definition. Okay. It has profound implications, but for now it's just out of nowhere. We say that the weights W1 to Wn are balanced if the following equality holds. For every j, Wj plus 1 transpose times itself is equal to Wj transpose. Okay? For every layer. This is just a definition. It, as I said, has profound implications. The reason why it's reasonable is because this either holds exactly or approximately under fairly common initialization schemes. Okay, if you initialize close to 0, then this thing is almost met. If you initialize to identity, which is kind of linear resnets, then it's met exactly. And what we show is that gradient flow over linear nets preserves balancedness. That means that if the weights are initialized to be balanced, they're going to stay that way throughout the entire optimization trajectory. Okay, gradient flow does not move arbitrarily in space. It follows certain trajectories, and in particular, balanced trajectories, if you initialize in these common ways. And this result allows us to address the following question. Suppose we optimize a linear neural net with gradient flow, okay? And we can ask, at every point in time, what is the equivalent linear model? Okay, we're optimizing over W1 to Wn, and what we ask is, what happens to the end-to-end matrix, the one that represents the entire mapping? How does that thing move in space? Okay, it does not follow gradient flow over L, over the loss, because we're not running gradient flow over the loss. We are over-parameterizing with a linear neural net and running gradient flow on that. So how does this thing move in space? And the result that we show using the balancedness property is the following. If the weights are balanced at initialization, then the end-to-end matrix follows what we call the end-to-end dynamics. It's what's written here. Okay? Ignore this blue term. You just get gradient flow. End-to-end matrix moves according to the gradient with a minus sign. Okay? Vec just means to take a matrix, arrange it as a vector. If you don't have the blue term, it's meaningless. The blue term is what manifests the fact that we used a linear neural net. This thing is a preconditioner. It's a PSD matrix. It has actually a closed form expression. Here it is. Please don't try and parse this. I'm just showing you to get a sense that it's not that complicated. This is the closed form expression for the preconditioner. Intuitively, what this preconditioner does is it promotes movement in the directions that you've already taken. And what do I mean by that? The preconditioner depends on the end-to-end matrix. And those singular directions that have a large singular value here, those are the ones, these directions are the ones where the gradient is going to be stretched more significantly. So if I start off near 0, I wander somewhere in space, I reached a point. Those directions where I've traveled a long distance, the gradient there is going to be pushed more significantly. Okay, that's kind of an intuitive way to describe what goes on here. It's possible to formalize this. Bottom line is that if we had a linear model and we add redundant linear layers, we turn this into a linear network, we are implicitly inducing a preconditioner, okay, that promotes movement in directions already taken. All of the results we're going to derive for optimization generalization rely on this theorem. Okay. All right, let's now move to optimization. This is going to be about half the time. I'll try to focus more on generalization because that's newer stuff. Yeah.
What happens if the initialization is not balanced?
Yeah, there are results for that too. We can talk about it. I'll actually show some of that where it's approximately balanced. I'll get to that. Thanks. Okay, so before we talk about utilizing our trajectory analysis for optimization, let's say a word about the alternative classic approach. Okay, if you will. One of the most prominent approaches for analyzing optimization in deep learning nowadays is to look at the geometry, and specifically characterize the curvature, the geometry of critical points. Okay, so you could have different types of critical points. I could have a local minimum that's good. The objective is close to the global minimum. I could have a local minimum that's bad. The objective is much worse. I could have a saddle with a negative curvature direction, so there's kind of directions of significant descent. That's called a strict saddle, or I could have a non-strict saddle, so it's very flat and you have to walk significant distance to start the descent. Formally, Hessian here does not have negative eigenvalues. Okay? And a result that was shown, yes, a couple of years ago by different groups and different flavors, many of them sitting here. Basically, if you sweep away a lot of the details, it states the following. If there are no bad local minima, right? So you don't have any points like this, and there are no non-strict saddles, you don't have any points like this, then gradient descent will eventually reach global minimum. Basically, it means that it's not going to get stuck in strict saddle points. Right? This is fairly encouraging. You can hope to maybe show convergence to global optimum just by looking at the geometry of critical points without considering the interplay between the model and algorithm and things like that. And indeed, there have been many works that have focused on establishing these properties, no bad local minima and no non-strict saddles. And you could maybe hope that maybe it's possible to prove convergence to global optimum for deep linear nets using this approach. But it turns out that this kind of approach hits a wall right at the outset. Because if you're interested in deep models, 3 or more layer models, then property 2 is just flat out false. It's not true that there are no non-strict saddles. For example, when all the weights are 0, all the second derivatives are going to be 0. And there you go, there's a non-strict saddle. So you can't really hope to use this kind of approach as is. Right? And what we're going to do is leverage our trajectory analysis. Okay, so this is the preconditioner. These are the dynamics that we derived. I didn't show you this, but it's pretty easy to see that if the end-to-end matrix is full rank, then the preconditioner is positive definite, meaning it's not going to kill this gradient. And so the descent is going to continue. The loss is going to decrease until one of two things happen. Either the gradient is 0, okay, and in that case, obviously, there's no movement. Or maybe the gradient is not 0, but the preconditioner killed it, and that's only possible if the end-to-end matrix was singular. Right? Usually the loss L is convex, so reaching 0 gradient means that you have reached the global minimum. So we get the following corollary for gradient flow. If the loss is convex and I initialize the linear net such that the loss at initialization is better than the loss of any singular matrix, so by going down, I'm never going to hit singularity. That's condition 1. Condition 2 is that the weights are balanced. Under these two conditions, gradient flow will eventually converge to global minimum. Okay, so we have a convergence result for gradient flow under two assumptions on initialization. There's no notion of computational efficiency, obviously, because this is a continuous optimization algorithm. In practice, we are interested in computational efficiency. And what we do is translate this result from gradient flow to gradient descent. This is the corollary for gradient flow. I will now wiggle a little bit with these conditions. I'll just write them differently. I'm not going to change them. Instead of saying that I want the loss to be better than the loss of any singular matrix, I'll say that I want it to be better than the loss of any matrix with a 0 singular value. Exactly the same thing. And for the balancedness, let's first plug in the definition. That's the definition of balancedness. And now instead of writing that these two things are equal, I'll just write that the norm of their difference is 0. Didn't change anything. And now we're going to slightly modify this and get a theorem for gradient descent. Okay, I'm just going to show you what we prove. I'm not going to actually prove it here. So first of all, the result for gradient descent, we proved it for L2 loss. It's possible to extend it to any strongly convex loss, but we showed it for L2. And these two conditions, we kind of defined discrete versions of them. And what do I mean by that? Instead of requiring that the loss be better than the loss of any matrix with a 0 singular value, I'll require a little bit more. I want it to be better than the loss of any matrix with a singular value that's smaller than C. And on the other hand, instead of requiring perfect balancedness, these norms to be 0, I will allow them to be small. Don't have to be 0. Okay, smaller than something that scales like C squared. Under these two conditions, gradient descent with a step size that scales like C to the 4th gives you linear rate convergence. Exponentially fast convergence. Loss iteration t scales like e to the minus constant times t. So we have here a result for linear rate convergence of gradient descent over arbitrarily deep models under two assumptions on initialization. Okay. What can we say about these assumptions? So first of all, we know that in some sense they're both necessary, meaning that you can't just erase one of these conditions and hope that the theorem will hold, because it does not hold. It's easy to come up with counterexamples. If you erase any one of them, then I can easily come up with an example where convergence is going to fail or even diverge. So you can't just remove them, you can maybe weaken them. The second thing we show is that for the case of output dimension 1, if you use a random initialization that's similar to what people usually use, but not exactly, without getting into the details, we call this random balanced initialization. If you use this thing, then with constant probability, both of the conditions are met, and you get linear rate convergence to global minimum. By constant, I don't mean some positive constant. I mean 0.25 or close to 0.5. So use this initialization, no assumptions at all. With probability close to 0.5, you get linear rate convergence to global optimum. Just a second. So what we have here is a result that shows efficient convergence of gradient descent on a compact model, one that you could actually fit in your computer. And that model is allowed to have 3 or more layers, an arbitrary number of layers. Okay? To my knowledge, this is the most general guarantee to date of this particular kind. Okay?
Could you say again what condition 1 means?
What it means? Well, it's a condition on how good your loss at initialization is. Okay? You need to be slightly better than matrices that are almost singular. Okay? It's some condition on to the question of how reasonable this is, then this is supposed to be the answer.
Well, that's in one dimension.
It is, yeah. The constant probability, that 0.25, is
But if I understand correctly, in one dimension, being singular means being 0.
That's right. So you need to be better than the origin for that
In
case.
origin, right? But in higher dimension, that becomes...
It becomes 0.5 times something to the minus n. That's correct. To the minus output dimension. That positive probability?
But you have to compare it to things that are much more complex. It's not just comparing to the origin, right? You have to compare it to any rank deficient matrix.
There's still a positive constant probability, but it depends on the output dimension in an exponentially bad way. Okay? So it's not that impressive for higher output dimension. But even for output dimension 1, to my knowledge, there are no results of this kind. Yeah.
So singular means each individual weight matrix is non-singular?
No, it's just the end-to-end. It's just in the end-to-end space.
So this means that you cannot have architectures where you reduce the dimension.
That's correct. There's no, this theorem, if the output dimension is 1, then that could never happen. But this theorem is not, these conditions are not going to be met if you have this bottleneck layer that's narrower than the input and output. Yeah, I'm trying to kind of circumvent some of the details.
When you talk about gradient descent, you mean full gradient, full batch?
This is for full batch.
Full batch only.
This result is full batch. Okay, and this was possible thanks to our trajectory analysis. Just looking at the geometry, kind of the classic approach, would not have given us this result. And what we're going to see now is something I think that is potentially more interesting and attests even more to the importance of trajectories, and that's the effect of depth on optimization. Okay, the classical view is that convex optimization is much easier than non-convex. Hence, optimizing a linear model is easier than optimizing a deep net, because this gives you a non-convex objective, whereas this gives you a linear one. That's the classical view, and what we're going to see is that through our trajectory analysis, we're going to see that this is not always the case. Sometimes it's easier to optimize these things than it is to optimize this thing. Okay? So I won't get into too many details because I want to get to the generalization part. I'll just state the result. Okay, this is our end-to-end dynamics in the discrete version. So there's discrete updates. Here's our preconditioner. And what we show is the following. For any p greater than 2, there exists setting where the loss is the LP loss. So it's based on the p norm to the power of p of the difference between true label and prediction. That's a convex loss. There exist cases with this loss where the end-to-end dynamics reach the global minimum much, much faster than gradient descent. So what this means is that there exist cases where I could run gradient descent over a linear model optimizing a convex objective, or on the other hand, do something crazy, which is to replace the linear model by a deep linear network and run gradient descent on that. The latter option would give me much faster convergence. There exist such cases. Okay, so this is non-intuitive. It goes against the conventional wisdom, but it might not be practical. The fact that there exist such cases doesn't mean that we encounter them in practice. The proof here cooks some certain data set that makes this happen.
Both of those are this fixed step size for gradient descent?
It's for fixed step size.
For both
Yeah.
dynamics?
Yeah. It might be possible to, we didn't invest too much thought into that, but it's for, what we showed is for fixed.
So P cannot be 2 here?
Sorry?
P cannot be 2?
No, it's not met. It's critical, the fact that it be greater than 2.
Okay.
And there's intuitive explanations for why. Because you need the loss to be very flat around the minimum and steeper around the edges. We kind of take advantage of that. I'm trying not to get into all these details, but it's not true for P equals 2. Yeah,
So the classical explanation for acceleration based on differential equations is that in gradient flow you get a first order. In the accelerated gradient
Yeah.
descent you get a second order.
yeah.
So by analogy here, if you're just using gradient descent and then let's say you overparameterize with, let's say just 2 layers, when you have that balanced conditions, you can eliminate and get a second order differential equation that is probably very similar to
So it's related to momentum, which is related to second order. There is a relation.
So I'm just confused as to whether you're saying you can construct examples versus the situation where this is generic because overparameterization will just increase the order of the differential equation.
I don't think this is generic. I know it's not true for P equals 2 or less. For P greater than 2, actually every setting we tried experimentally, this did happen. I don't think this is generic. I think you could maybe, well, I could come up with data sets where it won't happen. Maybe in a random data set it will. But we don't have that kind of result right now. To get a sense of how realistic this is, how common this situation is in practice, we run experiments. We ran a lot of them. I'll just show you the basic one. This is a regression problem from UCI Machine Learning Repository. We use L4 loss because we need P greater than 2. And this is what you get where you compare a 1-layer model, in blue, that's a convex loss, versus a 2-layer model and a 3-layer model. These are non-convex objectives. And you see that the loss decreases much faster. This is log scale. So in this particular case, adding depth speeds up gradient descent even without any gain in expressiveness and despite the fact that it introduces non-convexity. Every single setting we tried with L4 loss or P greater than 2, this happened. This also happened with nonlinear models. And I recently heard that someone took this idea and applied it to more large-scale settings. I didn't see the paper yet, so I hope it'll be out soon.
So the number of parameters for the 3-layer is higher?
That's a great question. Yeah, so and it is higher, but just to make that point, in this particular case, this is output dimension 1, and every layer is just a scalar. So it's almost the same. This is like 1,000 parameters, this is 1,001, and this is 1,002. So even if you divide by the number of parameters, it's the same. OK, let's move to the new stuff, generalization. We're going to look at a setting where generalization carries a very concrete meaning, and that is matrix completion. Okay, it's a classic problem. I get a subset of entries from some unknown matrix, and I want to complete the entries that I haven't seen. It has a lot of practical applications, as we know. And this can be seen as a supervised learning problem. Okay? I can think of any entry that I observe as a training example, and every entry that I did not observe as a test example. And generalization means recovering the test or being accurate on the test examples. Okay? Obviously, you need to assume something about the ground truth matrix, otherwise you can't do anything. And the baseline assumption is that the ground truth matrix is low rank. Okay? And there's a classic algorithm. I'd say by now it's classic, by Ben and Candace. And essentially what it states is the following. If I look at the set of matrices that agree with the observed entries, and from this set I choose the one with minimal nuclear norm is the sum of singular values, that's a convex program, then under certain technical assumptions, let's put them aside, because they are in some sense rare, if I have enough observed entries, then I will get perfect recovery. Okay, so a convex program would give me perfect recovery if I have sufficiently many entries, which is the minimal number that's needed times some logarithmic factor. And for this reason, this matrix completion problem is often regarded to be solved. But what we're going to see is that this, in practice, requirement for sufficiently many observations makes a difference, and there are cases where other algorithms do a much better job than nuclear norm minimization. Okay, we'll see that. What we're going to focus on is the use of linear nets for doing matrix completion. Okay, let's start with the two-layer case, because that's already a classic algorithm. In that case, I parameterize the ground truth as a product of two matrices, W1 times W2. Right? I can constrain the shared dimension and thereby force a low rank, or I could not do so. In any case, this algorithm is called matrix factorization, okay, running, like optimizing over this parameterization. And there's an empirical phenomenon that I think is fairly known, but Nathi's group, I guess, put the spotlight on this thing. And that is that if you run gradient descent over this parameterization with a small step size and initialization close to 0, then even if I didn't constrain the rank, a low rank matrix is going to be found. Matrix factorization does a good job in recovering low rank matrices and doing matrix completion. There is some implicit regularization at play. Okay? And the conjecture that they made is that in this case, gradient descent with small step size and initialization close to 0 over this matrix factorization implicitly realizes the classic convex algorithm. Okay? Implicitly, it finds the minimal nuclear norm solution. And they actually prove this for a certain specific setting. Right? So what we tried to do is build on this great work and look at what happens when you have n layers, not just 2. Okay? In this case, I parameterize the ground truth as a product of n matrices. Right? And we call this, unsurprisingly, deep matrix factorization. Okay? And the first thing we did was run an experiment. Okay? We ran matrix completion and compared deep matrix factorizations to shallow ones when the step size gets smaller and the initialization becomes closer to 0. So this is what you see here. Okay? We're completing a matrix here. This is depth 2, depth 3, and depth 4. X-axis here, that's the standard deviation of initialization. You can see what happens when it gets smaller. There are actually two curves here. They're almost one on top of the other, but they correspond to different learning rates. So you can see what happens when that gets smaller. And in this case, depth 3 and 4 significantly outperform depth 2. So in this case, depth enhanced the implicit regularization towards low rank. And what we were interested in is trying to theoretically analyze this phenomenon. Okay? The first direction that we went to is to follow the great footsteps of others. Okay, the conjecture that was made by Gunasekar et al. By a group in TTI is that the implicit regularization with depth 2 boils down to minimizing nuclear norm, which is a surrogate of rank. And what we initially thought is that maybe because we see that deeper models give you a lower rank solution, then maybe with a deeper network, there's some other norm or quasi-norm that's being minimized, which is closer to rank than nuclear norm is. Here's the most straightforward example, Schatten P quasi-norms. Okay, the Schatten P quasi-norm of a matrix is the sum of the singular values to the power of P. Okay? For P equals 1, this is exactly nuclear norm. That's what, according to the conjecture, corresponds to depth 2. And for P smaller than 1, this is a quasi-norm, and it's actually closer to rank than nuclear norm is. So what we initially thought is that when I add depth, I am taking P from being 1 to being smaller. Okay, that's what we initially hoped to show. But things did not exactly pan out as we planned them to, okay, which often happens. The first result we ended up proving is that in the particular case where Gunasekar et al. Proved their conjecture, nuclear norm is being minimized not just with depth 2, but with any depth. All of the depths minimize nuclear norm. And we also show that there are certain instances of this setting where minimizing nuclear norm means that you're provably not minimizing any Schatten quasi-norm, not even locally. So this means that what we hope to show, that the implicit regularization with depth is equivalent to Schatten quasi-norm minimization, or maybe even locally, that's not the case. We know for a fact that this is not true. On the other hand, if you kind of adopt the lens of Gunasekar et al., then maybe you end up with a different conjecture, and that is that all the depths actually minimize nuclear norm. Okay? So then we came up with kind of maybe this direction. But this does not comply with our experiments. Our experiments show that depth gives you closer approximation of rank. So what's going on here? Okay, so what we did next is kind of more careful experimentation of this nuclear norm minimization idea. Okay, this is a setting of completing a rank 500 by 100 matrix. Right? And we start with a case where you observe a lot of entries. Okay, so 100 by 100 rank 5 matrix. So you need about 1,000. There are 1,000 degrees of freedom, but we use 5,000 observed entries here. We compare nuclear norm minimization to linear nets of different depths. This is the reconstruction error. That's the nuclear norm of the final solution. And this is the effective rank, which Peter mentioned. You just think of this as rank, some continuous approximation. And in this case, because there are a lot of observed entries, minimizing the nuclear norm indeed gives you an almost perfect reconstruction error. So it finds the grand truth. Right? The nuclear norm is 221, and the effective rank is 5, which exactly complies with the rank of the grand truth. Linear nets in this case also give you a very good reconstruction. Not as good, but almost perfect as well. So obviously they found the same matrix. So the nuclear norms are going to be the same, and so are the ranks. So in this case, there is a correspondence. These linear nets of all depths indeed minimize the nuclear norm. Okay? But nuclear norm here, minimizing nuclear norm, finds the grand truth. So we can't really distinguish between nuclear norm minimization and maybe there's another implicit regularization that pushes these models to low rank. You would get to the same matrix. So on the way, I would also minimize nuclear norm. But that might not be the driving force. Okay, and to get a more kind of fair comparison, we look at a setting with a smaller number of entries. And here, nuclear norm minimization does not give you a very good reconstruction. The default is 0.8. This is 0.1. The nuclear norm that's found is 210. It's lower than before, but the rank is higher. So by focusing on nuclear norm minimization, it kind of missed the low rank. It got in rank 9. And in this case, linear nets give you better reconstruction error, especially depths 3 and 4. And they give you a lower rank. Here it's like almost perfect reconstruction. And the nuclear norm is higher. So they seem to give up on the nuclear norm minimization in favor of lowering the rank. Just a second. So in this case, we kind of interpret this as a discrepancy. And this happened in every setting we looked at where the nuclear norm does a poor job in reconstructing. Yeah?
So all these are without any noise in the elements, right?
Yeah.
Did you run any experiments with any kind of noise?
No.
Because when you have
Did matrix set? No, we didn't.
depth 3 and 4, it is presumably much more, at least intuitively more sensitive to
Well, it's not a matter of the idea is that they find a lower rank solution. You can argue if that's accurate or not with respect to what you want to recover, but we didn't play with these settings
So there was no noise in the element.
in this experiment. No. Yeah, Renee.
Wouldn't this suggest that there is a regularizer that changes with the number of observations maybe, and as the number of observations passes the threshold, you get the nuclear norm?
It might be. But what we are kind of saying here is that sometimes it's nuclear norm that's being minimized, sometimes it's something else. Maybe there's this kind of bimodality where after some threshold it becomes this norm, afterwards it's that.
But the P of the Chatten norm couldn't be a function of the...
No, I know it's no Schatten quasi-norm. That I know. But maybe it's something else. The kind of conclusion we reached is that maybe it's just not possible to capture everything that's going on with a single norm or quasi-norm. And that kind of led us to resort to move back to our trajectories and see if we can show something using that kind of dynamical analysis. Okay? So this is our implicit preconditioner. Here I'm marking in green, that's the end-to-end matrix. And what we're going to look at is what happens to the singular values of this end-to-end matrix. We would like to somehow show that there's a kind of implicit tendency towards low rank, meaning that the singular values, the gaps are opened between the singular values. That's kind of what we were hoping to show, and actually that is what we discovered. Sigma r here, these are the singular values of the end-to-end matrix, and UR, VR, these are the corresponding left and right singular vectors. Okay? The result that we derive for the dynamics of the singular values is what's written here. Okay? Ignore this brown term for a second. See that the movement of a singular value is just minus the projection of the gradient onto the corresponding singular component. Okay? The only place where depth n comes into play in this equation is in these factors. Okay? If n equals 1, then these factors reduce to 1, they disappear, and all you get is this projection. That's what governs the dynamics of singular values. If I start introducing depth, then these factors come into play. Okay? And while these constants don't make any difference because I can absorb them into the learning rate, these coefficients do make a difference. Okay? When a singular value is small, then this coefficient attenuates the movement. It makes it move much, much slower. On the other hand, if a singular value is large, then its movement enhances. It moves much, much faster. And the larger n is, the greater the power is here, so the more significant the effect is. Okay, and this is what happens when you optimize a linear net over any loss. And suppose you're optimizing some underdetermined loss, like in matrix completion, and you initialize close to 0, then what we would expect is that when the singular values are small after initialization, they're barely going to move. And then each singular value, once it reaches a certain threshold, it'll start moving rapidly, shoot up. And that ultimately will give you a low-rank solution because most of the singular values stayed close to 0 and only a small number of them shot up. And this is what we observed in every experiment that we ran. Okay, this is matrix completion. This is for depth 1. This is how the singular values move. There's no implicit regularization. This is depth 1. Okay? In the unobserved entries, you're not learning anything. And all the singular values move together. You don't get a low-rank solution. This is what happens when you add a layer. So the smaller singular values move much less. Okay? And these singular values, the leading components, once they become larger than some threshold, they start moving much faster, and you get something that's closer to low rank. And indeed, the reconstruction error is much lower. And if I add another layer, then this becomes even more significant, and the smaller ones barely move at all. And I get a very low-rank solution, and this gives me an almost perfect reconstruction. Okay, so this is kind of an empirical illustration, just a second, of the intuition. And for, you know what, yeah, go ahead.
I'm curious about when comparing the dynamics for different depths. If I'm understanding correctly, you're saying that infinitesimally, so there are two things that happen. The singular values, I mean, the strength or singular values change,
Yeah.
but also the singular vectors.
Yeah,
So you're saying that the infinitesimal change in singular vectors does not depend on depth?
No, it also does. There's kind of, we also characterize its movement as well. I'm just not talking about it, but there is a non-trivial dependency there. Yeah, it's not like there's a complete decoupling. It's a good question. Yeah. So this kind of analysis in general it's not as elegant as saying that some norm is being minimized, obviously. Usually in classical learning theory, when we regularize, we use some norm. So it's natural to think that maybe deep nets implicitly do this. It would obviously be a much better outcome than having a dynamical analysis. But what I'm arguing is that there's no reason to believe that, that it's possible. Okay, the fact that we're explicitly regularizing with norms does not mean that the implicit regularization with deep nets does something similar. It could be different. And looking at the trajectories is a way to somehow take into account all of the relevant details. Okay? For the special case, super simple, just a second, of one observed entry, we can actually give closed form expressions for the dependencies of different singular values. We know that for depth 1, the relationship is linear. So if one singular value gets larger, the other one can grow linearly, grows linearly with it. For depth 2, it's polynomial. So if this singular value grows, this one could grow like square root, things like that. And with higher depths, it becomes asymptotic. So if this singular value could be huge, this one would still not pass some threshold. Overall, we see here that depth leads to larger gaps between singular values, which means lower rank. Yeah?
What is the x-axis of those graphs on top?
It's iteration. This is the course of learning.
Why is it not an integer?
Times 10,000.
Times 10,000. This is okay. All right, so let's conclude. So recap is the main argument or position that I'm making is that understanding optimization, generalization, and deep learning might not be possible through the language that we've developed for classical learning. And in that case, it might be beneficial to analyze the trajectories of gradient descent. That's the entire course of learning, the dynamics of what goes on there. We try and make the case through deep linear neural nets. We analyzed the trajectories and showed that depth induces a preconditioner that promotes movement in directions already taken. We used this for optimization. We derived a guarantee of efficient convergence to global minimum, which shows you fast convergence over an arbitrarily deep model that's compact and can fit in your computer. This is the most general guarantee of that kind that I'm aware of. And more surprisingly, we saw that in this case, depth can actually accelerate convergence, even though it doesn't give you anything in terms of expressiveness, and despite the fact that it introduces non-convexity. And for generalization, our trajectories show that depth enhances an implicit regularization towards low rank, which for problems such as matrix completion amounts to better generalization. Okay, and just a word about the future. So we talked about linear nets, which are nice, a great theoretical tool, but at the end of the day, these are not the models that we usually run in practice. We're interested in nonlinear nets. And it's difficult to analyze nonlinear nets with ReLU and things like that. It's not analytical. But there's another type of nonlinear neural nets, which I believe are much more in reach. And we saw that linear neural nets, they correspond to matrix factorizations. And in the kind of language of decompositions of multidimensional arrays, this could be plotted as this chain. Every node here corresponds to a matrix parameter. And this graphical language allows us to describe not just matrix factorizations, but tensor factorizations as well. Factorizations of high dimensional arrays. And there are different topologies like trees and trains and things like that. And what colleagues and I in the Hebrew University have shown a few years back is that just like matrix factorizations correspond to linear nets, tensor factorizations correspond to arithmetic nets. Arithmetic nets are nonlinear models. Okay, so if you have a tree factorization, that corresponds to a convolutional net, and a train factorization corresponds to a recurrent net. These networks have a structure that is it's actually identical to practical models that people use, but there's one difference, and that is that they're arithmetic. Okay, the nonlinearities are only based on products. These are kind of polynomial networks. So they're much more algebraic in nature, but they're not exactly the type of models that usually people use. But nonetheless, they do work well in practice. For example, on SciFar, they reach over 90%. And they are more amenable to theoretical analysis. So I believe these kind of models could be the next step beyond linear nets. And we actually started doing this and analyzed the trajectories. And at least some of the results for linear nets transfer to these models as well, like the notion of balancedness and things like that. So I hope that maybe in the near future, we'll have some results on the trajectories of these models and be able to say more about optimization and generalization for a nonlinear model that's not exactly what most people use, but it does work well in practice. And with that, I'll conclude.
questions?
So I have a question regarding your main hypothesis. So it seems to me like you're associating to every point in the optimization manifold a positive definite matrix.
Yes.
So can we not derive the same results by a global structure, a global Riemannian structure instead of
Great question. That's
associating something which seems to depend.
it relates to mirror descent and stuff. That's ongoing work. Let's talk about it offline. But there is something you can describe. What did I do? I took a model, a linear net, and I replaced that by an equivalent algorithm. I said that this linear net, gradient descent over the linear net, can be thought of as some other algorithm over a linear model. Turns out that I could even do more. It's equivalent to gradient descent over a linear model, but with an underlying metric that's different.
So let's thank Nadav again. Okay, so our next speaker is Misha, and she will talk to us about